Hello learners, we are back with another video. In the last video we studied the different terminologies of motion and we also analyzed the different graphs for different kinds of motion. So in this video we will start with a problem that will help you recall all the concepts we studied in the previous video and also to build new information as well. So let's start. So we have a question which states, analyze the following BT graph and plot the XT and the AT graphs for the same. First, pause this video for a few minutes and try to think of the solution on your own. Okay, so let's solve this now. So here is our BT graph, and if you see, our graph can be divided into three sections. See, 1, 2, 3. So let's try to solve each part separately. Okay, so for the section 1 or the part 1, our graph is like this. So here we can see, since our velocity time graph is a straight line, can you tell me which kind of motion is this? Yes, it's a constantly accelerated motion or uniform acceleration. So in a uniformly accelerated motion, we know that the AT graph is a horizontal line coinciding at the initial acceleration. And from the slope of this graph, we can also find the initial acceleration as well. The slope of this graph will be the final value of the y-axis, 6, minus the initial value of the y-axis, divided by the final value on the x-axis, minus the initial value on the x-axis. So, this is 1.5 meter per second square. So here is the AT graph of our part 1. Now let's try to solve for the XT graph. Here we can see. Now if you recall from the previous video, I told you how to find the distance traveled in a uniformly accelerated motion. Can you tell me how? From the BT graph, it can be easily calculated as the area under the graph. And in this case, the area which gives the distance traveled will be half into the base of the triangle, that is 4, multiplied by the height of the triangle, that is 6. So the distance traveled would be 12 meters. And we also know that the position time graph of uniformly accelerated motion is a parabola. So for this interval we can write as this. And how much is the distance traveled? That would be 12. Clear? Let's head on to our part 2 now. So the part 2, if you look closely, it's a horizontal line. So which motion does this represent? Yes, it's representing the uniform motion since the velocity is constant. Uniform, constant velocity. So, if you want to calculate the AT graph from this, can you think of how we should do that? Since the velocity is constant, what do you think will be the acceleration? Yes, you guessed it right. Acceleration for constant velocity will be 0, since there is no change in velocity as the time passes. So AT graph will be a line coinciding the time axis, that is at 0. So now let's plot the xt graph for this. And here we know, just like we saw the previous question, the area under the curve will give us the total distance traveled. In this case, the total distance traveled will be again the area of the rectangle ABDE, 10 minus 4 times 6 minus 0. So our distance traveled is 36 meters. Again, so for a constant velocity motion or uniform motion, we know that the xt graph is a straight line. From the previous part, we know that our initial position was 12 meter, and now we traveled 36 meter at a constant velocity. So our final velocity would be 12 plus 36, that is 48 meter. So this is our xt graph or the distance graph for the second part. Now let's come to the part 3. Here we are given a uniform or constant retardation. How so? Because you see the velocity of the motion of the graph is decreasing as the time passes. So our acceleration is negative. So if we write the AT graph for this, and we take this value as a 0, then an acceleration would be a negative value, and let's calculate that first. The acceleration for this would be the final value of the y-axis. Now here it is 0 minus the initial value of velocity on the y-axis, that is 6, divided by the final value of the time, that is 16, minus initial value of the time, that is 10. So this is minus 1 meter per second square. And that's our retardation as well. Now if we calculate the xt graph for our part 3, if we draw the xt graph for the part 3, we know that it is again a parabola, but the final position would be a constant value. So after part 2, our initial position was 48 meters. And now if we calculate the area of the part 3, that would be the distance traveled in third section. So our distance traveled would be half times 16 minus 10 multiplied by 6. This gives us 18. So our final value would be 48 plus 18, that is 66 meters. Thus, if we combine all these graphs, we can write the final AT and xt graphs. So the AT graph would be the acceleration in the initial part, that is we calculated as 1.5. So the starting acceleration is 1.5. Till time t is equal to 4, and then it dropped to 0 since the second part was constant velocity motion, which continued till time t equal to 10, and then from time t equal to 10 till time t equal to 16, we had negative acceleration, or since the motion was constant retardation, at a value minus 1. So this is our final AT graph. Similarly, we can plot our xt graph as well. So in the first part of motion from time t equal to 0 till time t equal to 4, we know it's a constant acceleration motion. So our xt graph would be a parabola having a magnitude of, and the final position we calculated was 12 meter. The next part of our motion was constant velocity motion. So the xt graph would be a straight line, if you recall, having the value of the maximum velocity, that is 6. So for time t equal to 0, for time t equal to 4, till time t equal to 10, our xt graph would be a straight line. And then after that, from time t equal to 10 till time t equal to 16, we have a constant deceleration or constant retardation, and also we calculated the distance traveled total would be 48. And beyond that, a total distance traveled, and beyond that the xt graph would again be a parabola, but it would attain a maximum value, which was 66 meters. So I hope this is clear how to solve such questions, and I'm also sure that you have revised your concepts from the previous video as well. So let's move on now. Kinematical equations. Okay, to study this topic, we first need to understand what kinematics is. So kinematics is nothing but a branch of science that deals with the study of motion. Okay, so when we study these kinematical equations, we use all these 5 variables, and if you call them one by one, it will sound like so what. So we also call them so what equations. This is a mnemonic just to help you remember what our variables are that these equations include. So our first equation is V is equal to U plus AT. V is equal to U plus AT, which means that if a body starts with the velocity U, initial velocity as you can see here, then if it's given an acceleration A under time t, then from this equation we can calculate the final velocity after time t. And how did we get to this equation? Well, it's all under the concept of this acceleration. Acceleration, if you remember, is nothing but change in velocity divided by the total time. And so, if you take the t there, you can write this as V is equal to U plus AT. That's how we derived this equation. For our second equation, we have S is equal to UT plus half AT squared. Now this equation tells us that if a body starts with an initial velocity u and it's given an acceleration a under a time t, then the total length or the distance traveled of the body will be s. How did we get to this equation now? So we came to this equation like this. If we take the average velocity, if you remember it from your previous video, the average velocity gives you is defined as the total distance traveled upon total distance time upon total time. So, and we also learned how to calculate the average velocity. We just take the both velocities, their sum, and divide by the number, that is 2. So this gives us the total distance traveled as v plus u by 2 multiplied by time. And if we substitute v, we take this value of v here and put it over here, then this gives us u plus at plus u divided by 2 multiplied by t. And if you rewrite this, you will get 2 times ut plus 80 square divided by 2, which is nothing but ut plus half 80 square. So that's how we derived our second equation. So let's now derive the equation 3, that is v square is equal to u square plus 2as. What does this equation means? So it deals with the final velocity and the initial velocity and relates them to the distance traveled along with acceleration. Now how did we get to this one? Let's understand. So if you recall, in the derivation of the previous equation, we calculated distance traveled as v plus u divided by 2 times t. And from the first equation, we can substitute the value of t as, first we write v plus u divided by 2, and we can write t as v minus u divided by a. So here we can write this as 2 times as gives you v square minus u square. We got to this using the algebraic identity of a plus b multiplied a minus b, which gives a square minus b square. Clear? So the equation turns out to be v square is equal to u square plus 2 times as. So that's how we derive our third equation. But this is not the only way to derive these equations. We can also derive them graphically. Let's see how. So can you guess which kind of motion is this? Yes, this is a constant accelerated motion. So let's try to derive the equations of motion or the kinematic equations from this graph. Firstly, we know that the slope of this graph is nothing but the acceleration. And we also know the area of this graph gives us what? Yes, the distance. So now we have all the Stewart variables. If you remember them, we have the final velocity, the initial velocity, the acceleration, the distance, and the time. So let's derive the equations now. So from the graph at time t equal to 0, our velocity is u, and at time t is equal to t, our final velocity is v. So if you find the acceleration from this, acceleration is nothing but the difference in the velocities, that is v minus u, divided by the total time for this the change happens, that is t. So we can derive our first equation, v is equal to u plus at. Okay, so we have derived first one and there are 2 more to go now. Now again, the distance traveled is nothing but the area under this graph. So S is equal to the area of the trapezium. Trapezium is nothing but a 4-sided figures with 2 parallel sides. Okay, so area of the trapezium is half times the sum of the parallel sides, which we can see this and this. And here we can calculate this length is u, the longer one is v, so we'll add them, and then we will take the height, that is time t. And what will we do next? We will replace this v with our first equation. This gives us half times u plus 8t multiplied by t. So again, this turns out to be ut plus half 80 square. So yes, we have derived our second equation as well. Now for the third equation, for that we will again take the distance. So S is equal to half times u plus v times t. And now, instead of replacing v, we will replace t here. So this gives us half times u plus v multiplied by v minus u divided by t. So now, just like we did before, 2 times as is equal to v square minus u square, again using the algebraic identity. So we can obtain v square is equal to u square plus 2as, and here is our third equation. So I hope this is clear how to derive the kinematic equations using a graph. Let's move on to our final topic now, that is uniform circular motion. Now this motion is a uniform motion, and what is a uniform motion? We said it has a constant speed. Also, you can see it's a circular motion, just like in this animation. So if we define it, what is it? A motion of a particle moving at a constant speed on a circle. Now notice how we are deliberately talking about constant speed here and not the velocity. You can also see from this animation that the velocity, which is a vector, that means it has a direction, changes at every point on the circle. So, in a uniform circular motion, the velocity does not remain constant. Only the speed, that is the magnitude, remains constant. So let's calculate how much this particle, as shown in this animation, travels during one complete circle. So, in a complete revolution, the distance traveled by this particle is nothing but the circumference of the circle, which is 2 pi r, where r is the radius of the circle. This r is the radius. And what will be the displacement? Think of it for a second. When I first told you about the definition of displacement, it was the shortest distance traveled between the initial and the final position of a particle. But for a complete revolution, if we take a complete revolution and we started from here, and again we reached here only, our initial and final position would become the same, and the difference would be the zero, because that's the shortest path. Thus, the displacement in a complete revolution is zero. So I hope you have understood all these concepts very clearly, and you can watch this video again to revise your concepts and as well as the previous one. And also you can log on to EduRev app and website to build up more knowledge from detailed documents and practice online tests for better practice. Thank you.